Hello friends, today we'll discuss about UV visible spectroscopy and wave nature and particle nature of the electromagnetic radiation with various types of electronic transitions. To begin with, spectroscopy. Spectro means the interaction. Interaction with what? Interaction of electromagnetic radiation, and scopy means the technique. So spectroscopy is the study of the measurement of amount of electromagnetic radiation that is observed or emitted or scattered by a sample to perform an assay. The sample to be analyzed will be taken in a transparent box. This is inside the spectroscopy machine. This transparent box is known as qubit. In this, the sample will be added. The monochromatic rays, that is electromagnetic radiation, are passed through this qubit. This radiation pass through the sample and the radiation which comes out of the sample are analyzed. These radiations may get absorbed by the sample and remaining radiations may get passed out. This is known as absorption. Or else these can get transmitted without absorbing by the sample. This process is known as transmission. So this is a diagram representing various types of radiations along with their wavelengths. The gamma rays are having wavelength 1 picometer to 10 picometer. X-rays are having wavelength 10 picometer to 10 nanometer, and far ultraviolet rays are having wavelength from 10 nanometer to 100 nanometer. The visible range of radiations. These radiations are seen by us. These are having wavelength from 200 nanometer to 1 micrometer. So what is an electromagnetic radiation? Electromagnetic radiation is a form of energy propagated through free space or through a medium in the form of electromagnetic waves. These waves contain both electric and magnetic waves. The electric waves are perpendicular to the magnetic waves. These electromagnetic radiation have dual nature, both wave nature and particle nature. That means these radiation behave as a wave and as a particle. So this figure represents electromagnetic radiation. It contains electric field and magnetic field moving in a direction. So this electric field is perpendicular to the magnetic field, and the electromagnetic radiation, it behaves as both wave nature and particle nature. That means it behaves as a like a wave and it behaves as a particle, a group of energy particles moving in a direction. These energy particles are known as photons. We'll see about wave nature of the electromagnetic radiation. So the wave nature means the electromagnetic radiation is in the form of a wave. This wave has some characteristics such as wavelength, speed of the wave, and phase, and the frequency of the wave. Frequency is defined as number of cycles of a wave passing through a point per second. So this is electromagnetic wave, and these are peaks of the wave which are known as crest, and the bottom of the wave are known as troughs. And the one cycle contains one crest and one trough. So this is one cycle of a wave. So number of waves which pass through a point per second is known as frequency and represented by symbol nu. And the distance between consecutive peaks, two consecutive peaks, is known as wavelength, or the distance between two consecutive troughs is the wavelength of the wave, and wavelength is represented by lambda. We will discuss about the wavelength and its relation with the frequency and energy. So a radiation which is having lesser wavelength will have higher frequency. That means more number of cycles of a wave through a point per second. A radiation which is having more wavelength will have lesser frequency. That means less number of cycles pass through a point per second. And you can also see the wavelength. It is the distance between two consecutive thrufts as shown in figure. Wave number, it is defined as the number of crests or thrufts in a given unit length of a wave. So we will discuss about the particle nature of the wave. So our electromagnetic wave behaves also as a particle. So it is described as particles of energy moving in a direction, and these particles are known as photons. So energy of these particles is equal to h into nu, where h is Planck's constant and nu is frequency. So higher the frequency, that means higher the energy of the electromagnetic radiation. The energy is directly proportional to frequency of the radiation, and h is the Planck's constant. So these photons, they do not have any mass and they also do not have any charge. So as I have explained you in the starting of the video, when electromagnetic radiation passes through a sample, it may get absorbed, or it may get transmitted, or it may get emission. The UV visible radiation, IR radiation, get absorbed by the sample, and the remaining unabsorbed rays are released out. This is known as absorption. Next, this electromagnetic radiation which pass through a sample, they may also get transmitted without absorbing into the sample. And next option is they may get emission. That means when we pass this electromagnetic radiation through the sample, the atoms get excited into higher energy levels. That means the electrons get jump from one shell to another shell, and these electrons which have jumped to the higher shell, they once again reach back to the lower shell. When they reach back to the lower shell, they release energy in the form of a radiation. So this process is known as emission. So they absorb energy from a radiation, move to higher energy states, and they again come back to lower energy states by releasing a radiation. So this release of radiation by atom is known as emission. So these electromagnetic radiation, they may be absorbed or transmitted, or emission takes place according to different types of electromagnetic radiations. Now we'll discuss about the electronic transitions. Closed shell electrons. These are inner shell electrons. So they are not involved in bonding, so that they need higher energy to get excited from one energy state to higher energy state. Single bonded electrons or sigma electrons. These are electrons present in saturated hydrocarbons. They are present in sigma bonds. They absorb energy from vacuum UV region having wavelength 10 to 200 nanometer. Non-bonding electrons. These electrons do not participate in any bond formation. They are present as lone pairs, and they are usually present in heteroatoms like oxygen, sulfur, nitrogen and halogens. They absorb the electromagnetic radiation in UV regions. They are having wavelength UV region 200 to 800 nanometer. Pi bonding electrons. These electrons are involved in pi bond formation, and they are present in unsaturated hydrocarbons. They absorb near UV and visible region of radiations having wavelength 200 to 800 nanometer. We have discussed about the electrons in different bonds and different shells, how they get excited, and the radiations which they need to get excited. Now we'll discuss from where to where these electrons get excited. Sigma to sigma antibonding transition. The electron in bonding s orbital is excited to corresponding antibonding orbital. For example, we have H2 here, and H2 sigma bond is represented in this way. This is a s orbital of one hydrogen, and this is s orbital of another hydrogen. So one electron from this hydrogen and one electron from this hydrogen is shared to form a sigma bond. When I pass electromagnetic radiation through this sample containing H2, these electrons get energy from this radiation, they absorb energy, and as a result they move into higher energy states and they form antibond. So this represents the antibonding of the hydrogen molecule. Here the energy required is large. UV visible region radiations are involved in this in the presence of vacuum. Next, N to sigma star transition. That means the saturated compounds containing lone pairs. These lone pair of electrons move into sigma antibond state, and this transition usually need lesser energy than sigma to sigma antibonding transition. So they are initiated by light of wavelength 150 to 250 nanometer. Compounds which are containing pi bond. When these compounds absorb the electromagnetic radiation, the pi electrons are excited into pi antibonding orbitals. This takes place in alkenes. Next, N to pi antibonding transition. An electron which is non-bonding lone pair electron gets excited into pi antibonding orbital, and this is known as N to pi antibonding transition. So the compounds which are containing double bonds along with the heteroatoms, in these compounds N to pi antibonding transition takes place. So these N to pi antibonding transition require minimum energy, and these transition are shown by the radiation which have longer wavelength around 300 nanometer. So you can see in the figure that sigma to sigma star transition requires more energy. Pi to pi star antibonding transition requires little less amount of energy, and N to sigma star antibonding requires further less amount of energy, and N to pi star antibonding requires least amount of energy.